We continue our study of how to describe data by looking now at different measures of variation, otherwise known as measures of spread. Variation is the single most important topic in statistics, so this is the single most important section in this course. This section presents three important measures of variation or spread. The first is range, then standard deviation, and finally variance. While these statistics are calculations, our focus will be on how to interpret those calculations and understand them more so than the computations themselves. As for the round-off rule for variation, it's very much the same as it was for measures of center. We want to take out the calculations to one more decimal place than what the original data went out to. First, let's talk about the range. The range is a very simple calculation, a very short way to talk about spread. Range is simply the difference between the largest value in the data set and the smallest value in the data set. So the maximum value minus the minimum value. Because the range does take into consideration the smallest and the largest values, it is very sensitive to outliers, to extreme values. In fact, it reaches out to the leftmost point and the rightmost point. Therefore, it is not resistant. It's very easily influenced by extreme values. It does not take every value into account. In fact, it only takes the most extreme values into account. Let's do a simple calculation with range. Here is a small data set. These are wait times for Walt Disney World, the Space Mountain ride, 50 minutes, 25 minutes, 75 minutes, and so on. If we were to look at the smallest value in this list, we find that it is 20 minutes, and the largest value in the list would be 75 minutes. So the range is found simply by subtracting 75 minus 20, or 55 minutes. Standard deviation, on the other hand, is a much more complicated calculation. What it is a measure of how much the data values in a set deviate from the mean of the data set, how far these data values are from the center. The standard deviation for a sample is denoted by the lowercase letter s. It is a sample statistic. The standard deviation for an entire population is denoted with this Greek letter, which is the lowercase letter sigma. It kind of looks like an O with a little tail at the end, but it's actually the lowercase letter sigma. And again, that is the symbol that we're going to use when we're talking about the population of the entire population of interest. So S is for a sample, sigma is for the population. They both denote standard deviation, just a difference between whether the values are coming from a sample or whether the values are coming from the entire population. This is the manual formula for calculating standard deviation. In fact, we have two different alternate formulas that give us the same result. The formula here at the top is the one that we're going to demonstrate through an additional YouTube video and in the example in the upcoming slides. We're going to break down that formula so we understand where those values are coming from in just a bit. The second formula is what calculators and computer programs are programmed with. So it's what we call the shortcut formula, but it's not a shortcut when we're making manual calculations, it's a shortcut for programming. Let's talk about some properties of standard deviation before we look at how to compute it. First of all, the standard deviation is a measure of how much the data values deviate away from the mean. And again, that's important for us to remember. We first have to look at where the mean is for the data and look at that center anchor as what we're trying to find distance from. So first we find the mean, we use that as our anchor point, and then we're going to look at distances for each of the data values from that mean. The value of the standard deviation is never negative, and it is only 0 when there is 0 spread in the data. And that, of course, occurs when all the data values are exactly the same. So the mean and all of the data values are one and the same. Larger values of standard deviation indicate that there is more spread, more variation. Smaller values of S indicate that there is less spread, less deviation. The standard deviation S can increase dramatically with one or more outliers. I think there's a simpler way for us to say this. Standard deviation is not resistant. It is susceptible. It is easily influenced by extreme values. And I think this makes sense because standard deviation uses the mean, which itself is not resistant. We talked earlier that the mean is easily influenced by either very small or very large values, those that kind of stand out from the rest of the pack. So if the mean is not resistant, if the mean is easily affected by extreme values, it makes sense that standard deviation would have the same disadvantage because it is calculated from the mean after all. The units of standard deviation are the same as the units for the original data values. So if your data values included minutes or feet or pounds or any other unit, standard deviation units would match that. The sample standard deviation S is a biased estimator of the population standard deviation sigma, and what this means is that values of the same standard deviation S don't necessarily center around the population standard deviation sigma. There's a way to kind of explain this a little bit better through a graph. If you can imagine a dartboard with a bullseye, what this would look like is that the bullseye would be the population standard deviation sigma, and that as we gathered samples from that population and calculated the sample standard deviations, those S values would not necessarily converge on the bullseye. They kind of would be all over the place. So that's what we say is a biased estimator. It doesn't come close to the bullseye. They kind of tend to be spread out. So there's a lot of difference expected from one sample to the next. All right, let's look at the calculation of standard deviation manually. We are going to use the first formula, and it all starts with calculating the mean of the data set first. So let's go back to looking at these wait times for the Space Mountain ride in Disney World. 50 minutes, 25 minutes, 75 minutes, etc. To find the mean, we add all those values and then divide by the number of values, which in this case is 11. So we find that the mean wait time is 39.1 minutes. Now we're going to subtract the mean, which we denote as this X bar. We're going to subtract the mean from each of the original data values. So the mean was 39.1, so we're going to do 50 minus 39.1. Separate from that, we're going to do 25 minus 39.1, 75 minus 39.1, etc. down the list. So here are those differences already calculated. Again, we subtract the mean, which we found earlier, from each of the data values, and then here's the list of all those differences. The next step is to square these differences. So that 10.9 will be squared, gives us 118.81. The negative 14.1 is squared. Recall that when we square a negative quantity, it becomes a positive product. So negative 14.1 when squared becomes 198.81. In essence, all of these squares are going to be positive, or the worst case scenario would be 0 if the difference had been 0. Next, we're going to add those squares. When we add those squares, here is the sum. Finally, we're going to divide that sum by our sample size n minus 1. So you might recall we have 11 data values in this example. 11 minus 1 would give us 10 in our denominator. And the last step is we're going to take the square root of this result. So when we take the square root of 274.091, we get our approximate sample standard deviation of 16.556 units. And remember, we're looking at wait times, which were in minutes, so our units are minutes as well. The rule of thumb that we're going to keep referring back to when it comes to interpreting standard deviation is as follows. This is something that we're going to continue seeing over and over again for the remainder of our course. So this is pretty significant, pretty important for us to stop and take a look at what this implies. The range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. The vast majority, such as 95% of sample values, are expected to lie within 2 standard deviations of the mean. So I want you to picture a number line where we have the mean labeled on the number line, and we've calculated our standard deviation for the data set, and we're going to take that standard deviation number and we're going to add it to the mean once, add it to the mean again, and then we're going to subtract it from the mean once and subtract it from the mean again. So now we have 5 values: the mean in the middle, 1 standard deviation above the mean, a second standard deviation above the mean, and then the same on the opposite side to the left of the mean, 1 standard deviation to the left and another standard deviation to the left. So we have 5 labels now on the number line. This is, again, one of the most important interpretations of standard deviation and the mean in terms of identifying where we think the line would be drawn as to values that don't surprise us. They're within the normal fluctuation that would be expected, and then values that kind of fall so far from where we would expect them that we raise questions and consider them to be interesting, unexpected, and in statistical terms, we call them significant. So that is a statistical term. So again, imagine the number line. Here is your mean, whatever that mean is. In this case, we can look at 39.1 minutes as being the mean wait time for the Space Mountain ride. And we calculate standard deviation, whether it be S for the sample standard deviation or sigma for the population standard deviation, and we add that standard deviation number to the mean, we would end up somewhere around here. And if we do that again, we'd end up at 2 standard deviations above the mean. Same thing to the left. If we subtract 1 standard deviation from the mean, we end up right around here where the cursor is. And then if we subtract another standard deviation from the mean, we end up here where this label is. So values that are within 2 standard deviations of the mean, either above the mean or below the mean, but they're within 2 standard deviation arm lengths, those are what we call values that are to be expected, part of traditional fluctuation. These values are not significant. However, values that are more than 2 standard deviations above the mean are said to be significantly high. Values that are lower than 2 standard deviations below the mean, those are values that are said to be significantly low. You might recall the simple calculation of range, simply the largest value minus the smallest value in a data set. It's crude, it doesn't tell us very much, but it can be used to give us a very rough estimate of standard deviation. If we take the range and divide it by 4, we have a very crude, not precise, but at least an idea of what our standard deviation might be. Recall that the range is very, very susceptible to extreme values. So if we do have some outliers, this estimation will not be as useful as if the range did not include outliers. In this slide, we're looking at how to calculate the standard deviation. If we have data values from an entire population, we really don't need to worry about this formula. in the sense that we rarely will have a census where we get data values from every object or person in a population. However, what we want to point out is that if we were to compute standard deviation manually, there is a difference here. First of all, we use the sigma label for standard deviation because this is a population parameter. It designates that this calculation includes all the values in the population of interest. So instead of S, we use the sigma label. And then another difference is, of course, the mean of the population is represented with the letter mu versus the X bar symbol is the mean of a sample. So you see that mu is a population statistic label, sigma is a population parameter label, I should have said. So mu is a population parameter label, sigma is a population parameter label, and then this capital N, which designates the population size, that is also a population parameter label. So sigma instead of S, mu instead of X bar, capital N instead of lowercase n, these are all values that come from an entire population versus a sample. Notice here that in the denominator we do not divide by the population size minus 1, where we did do that when we were calculating standard deviation for the sample. So that is another difference between the two formulas. Again, you should not have to use this formula in practice. We're just trying to point out some of the differences. Now finally, let's talk about variance for a sample and for a population. Variance is a set of values that measure the square of the standard deviation. So the sample variance is S squared, population variance is sigma squared. It's that number that you get in the calculation before you take the square root. So sample variance and population variance, they tend to be larger numbers than standard deviation. And let's look at what we would use this for in terms of interpreting spread. Before we do that, let's look at the labels again. S is the label for a sample standard deviation. S squared would be the label for sample variance. Sigma is the label for a population standard deviation, and sigma squared would be the label for population variance. So again, these two first values are sample statistics. The last two values are population parameters. All right, let's take a look at the empirical rule. And this is something that we're going to discuss kind of at a high level for now. We will come back to this in much more detail once we get into a later chapter of our course. But for now, we're going to look at a normal distribution, which is a bell-shaped distribution. And we're going to look at what happens as we travel to the left and to the right of the mean. So again, picture a number line where we know where the mean is and we have that labeled, and we extend out to the right one standard deviation jump, and to the left of the mean another one standard deviation jump. Well, within that window, we expect to have about 68% of all the data values in our set. If we extend a little bit further, so that we're extending 2 standard deviations to the right of the mean and 2 standard deviations to the left of the mean, of course we have a much wider window, and now we expect to include about 95% of all the values in our data set. This is what we saw earlier in that range rule of thumb. And finally, if we extend out further, 3 standard deviations to the right and to the left of the mean, we have a much wider window. Now we expect to have almost all the data sets. Approximately 99.7% of all the data values would fall within 3 standard deviations of the mean. Here's a visual representation of what we just saw in this slide. Let's see if I can move this out a little bit. So again, here is a number line where we have labeled the mean, and in this slide we're looking at sample values because we have here X bar. So here's where the mean is in the number line. S is our sample standard deviation, so if we add X bar and S, we would end up somewhere around here on the number line. And if we subtract S from X bar, we end up right around here. Well, within this window, we expect approximately 68% of all the data values in our set. And remember, the height here represents frequencies, right? So we expect to have many values in our data set that are close to the mean, and then still a good number of data values that are a little bit higher than the mean, some values that are a little bit lower than the mean, but those frequencies start to drop as we get further and further away from the mean. Now if we extend further, 2 standard deviations to the right, here's that label right there, and if we extend 2 standard deviation jumps to the left, right around here, we now expect to have approximately 95% of all of our data values within that window. And finally, if we extend really far out, 1, 2, 3 standard deviations to the right, 1, 2, 3 standard deviations to the left of the mean. Now we expect to include almost all of the data. Notice that there's very little going on beyond those labels, right? A very, very small amount of data would fall outside of that window. So approximately 99.7% of all our data values are expected to fall within 3 standard deviations to the right and to the left of the mean. Again, this is called the empirical rule, and we are going to refer to this quite frequently for the remainder of the course. Let's use an example to illustrate how to use the empirical rule. Here we have IQ scores known to have a bell-shaped distribution or a normal distribution. The mean is 100, standard deviation is 15. The question is, what percentage of IQ scores fall between 70 and 130? So first we're going to think about the fact that we know the standard deviation of 15, we know the mean is 100, and we know that this is a bell-shaped distribution. That means that the empirical rule applies. We need to find out where 70 would fall in relation to the mean, where does 130 fall in relation to the mean, so that we could see how to apply the empirical rule. Well, turns out that 70 is exactly 2 standard deviations below the mean. Why? Because if the standard deviation is 15, 2 times 15 is 30. 30 represents 2 standard deviations. So the mean is 100. 2 standard deviations below it would be 70. And actually 2 standard deviations above it would be 130. So because 70 and 30 are 2 standard deviations to the left and 2 standard deviations to the right of the mean, we saw from the empirical rule that approximately 95% of all IQ scores would fall between these 2 numbers. Lastly, we're going to talk about the coefficient of variation as another way to interpret data and describe what we're seeing. The coefficient of variation, also denoted as CV for short, is a non-negative sample or population data calculation, which is expressed as either a percent or as a decimal. It describes how the standard deviation and the mean relate to one another. It's a very simple calculation. It's simply the standard deviation divided by the mean multiplied by 100. Notice here that we have the coefficient of variation for a sample. So we have the sample standard deviation S divided by the sample mean X bar times 100. And here's the coefficient of variation for a population. This is sigma, the population standard deviation, divided by mu, the population mean, times 100. The round-off expectation for the coefficient of variation is that we go out to 1 decimal place always. Again, these are percentages, so regardless of the original data values, we only need to go out 1 decimal place in the percentage calculation.